Okay, so let's go ahead and get started. I'm hearing all this two's complement chatter.
-1.
I did say, didn't I say that lab 4 really tests your knowledge of two's complement? Let's start seeing two's complement in your dreams. Okay, so today's class, the big topic is finite state machine, okay, and FSM. You know what it is, then how you would model it, system Verilog, and I'll show you that through an example. The activity today has to do with modeling an FSM and system Verilog, along with something called the state diagram. Okay, but before we get to the FSM, there's a couple other things I just want to go over. One is what a clock divider is, and you know, I want to go through the code that implements this clock divider, and then I just want to spend a brief amount of time on what a counter is. Okay, both of these, the clock divider and the counter, they're often needed in the final team project. Now, the final team project, you get to decide what to do. So, you know, it depends what you decide to do. But a lot of times, like, people will do like some kind of stopwatch or a clock of some sort. And like a lot of times they'll do a game where you want to keep track of something. And, you know, that's where counters can be used. Also, the clock divide, a lot of times that's also used in any sort of timing circuits like counters and stopwatches and stuff like that. So, and also the clock divide is part of lab 6. Okay, although we give you the code for that clock divider, but anyway, that's where I want to start. So first of all, you all should have a handout. You should have a handout that has the code for module clock divider. So as I talk about this clock divider, you know, make sure you have this handout that you can refer to. So first of all, this is the high-level black box diagram of a clock divider. It just has one input, normally labeled clock, like you see here, CLK, and then one output that I labeled S, CLK, where the S stands for slow. Okay, because what a clock divider does is that it takes in a frequency, you know, a square wave frequency, and it will cut it down to a lower frequency. What's the significance of 100 megahertz in this class? Last class I talked about this. Like, what's the significance of 100 megahertz in our class? The processor of what? The processor on what? Of what you're using this quarter? Basis board, right? Exactly. This is the operating frequency. The FPGA that's on the Basis 3 board. And then we've also talked about this also last time. What's the period of something that's at 100 megahertz? One over. Okay, and what did that come out to? Say it again. 10 nanoseconds. Again, that's the reason why in the sim file you have the number sign 10 for each of the test cases, because that's creating a 10 nanosecond delay between each test case. And 10 nanoseconds corresponds to one clock cycle. So, you know, we're doing a test case, waiting a clock cycle, do another test case, wait a clock cycle, do another test case. Okay. All right. Now, something you haven't seen before that's part of the code for this clock divider is at the very top. After where you see the name clock divider, the module name, you have this number sign, and then in parentheses, parameter max count equal to 1. This is a way that you can, you know, declare like a variable that we call a parameter, and then also set it to some default value. Now, a lot of times where it can be helpful to have a parameter like this is that, you may have a case where your design has 5 different clock dividers, right, within the same diagram, but each one needs a different parameter in order to get the frequency we want. Okay, and you'll see how this number that we set the max count to, you'll see how it affects the frequency of this slow clock. Okay, well, if you had multiple clock dividers in a diagram that you were building, well, you can easily change the value of this parameter in the top module where you make the connections. All you would have to do is in the line that's making the connections, in between the file name and the label, you would just put $sign and then put the new value that you want for that parameter. So you see, that can be helpful because that way you just have one file that has the default value, and then all you got to do is just make a simple edit in your top module to get a different parameter value, as opposed to having multiple clock dividers where they have different default values. Okay, so you just save yourself some files by doing it that way. Okay. All right. So now, if you take a look at this code here, you can see that the inputs and output, the input clock and the output S clock are defined. Notice that S clock is initialized to 0. Okay, so this is a way that you can initialize an output to 0 is right in the declaration of the output. And then you can see we have an internal signal here called count. How many bits is count? 30, right? It's 29 to 0, so it's 30 bits. And we're just using this count as an integer. So it's unsigned. So what's the range of an unsigned number if it's 30 bits? It goes from what to what? It's going to go from 0, right? All unsigned have a minimum value of 0. How would you figure out the top number?
It's 2 to the
Okay, is it just 2 to the 30? Yeah, -1, yeah. Yeah, the way I remember is I just think a smaller number of bits. Like I think 4 bits, and I know with 4 bits I can go from 0 to 15, right? So to get 15, it would be 2 to the 4 minus 1. Yeah, so no matter how many bits you have, if it's unsigned, you would figure it out like this. Now, if you actually did do 2 to the 30, it comes out to 1,073,000,000. What is it? It's like 741,824, I think. Yeah. So I mean, it's a big number. So that's what 2 to the 30 is. So you subtract 1 from that, right? So it'd be 1,073,741,823. That would be the top number. Okay. The reason I show this is, you just got to make sure that you have enough bits for that count for whatever number you're going to use for max count. Okay, and you'll see why here when we run through the rest of the code. All right, so after count is declared and it's assigned 0, now comes the always FF, right? And that should be no surprise because this has a clock, right? Anytime you have a clock signal, that means it's sequential, like we talked about earlier. And then what's the significance of the pause edge clock within the parentheses? What's the significance of that? Right, that on every 0 to 1 transition of the clock, the rising edge, that's when the always FF block, what's inside, is going to be evaluated. So, here's our clock signal, right, going into this module. And, every positive edge, that's when that always FF is going to be evaluated. Okay. So let's look at what's inside the always FF. Well, the first thing is we're incrementing count by 1. And again, count was initialized to 0. So on the first clock edge of the clock, count is going to go to 1. And then you got an if statement where you're comparing count to max count. And let's say we make max count 50 million. Okay, now again, one way we could make it 50 million is just by changing this default value from 1 to 50 million. Another way would be in the top module, we could do it if we wanted, right? If we wanted to leave that as a default of 1. Okay, but however we do it, we make this 50 million. So of course, 1 is not equal to 50 million, right? So it's not going to evaluate what's in the if, right? Because it's not true. And on the next positive edge, well, we'll increment count by 1 again, right? And it's going to be 2, right? That's not 50 million, of course. And it's just going to keep going. And oh, I forget to write it down here, but like I said before, S clock has been initialized at 0, right? So it starts at 0 and it's going to stay 0 for 50 million positive edges or 50 million clock cycles. And each clock cycle has a period of 10 nanoseconds. So to figure out how long S clock is going to stay at 0 or how long count doesn't equal max count, we just got to take 50 million times 10 nanoseconds. So what is that? You take 50 times 10 to the 6th power times 10 to the minus 9 power. What are we going to get? You don't need a calculator for this, do you? What's 50 times 10? You all know what 50 times 10 is. 500. And then what do you do to these exponents when you multiply? So what is it going to be? What are we going to have? 10 to the minus 3. Minus 3 is what? How many milliseconds, right? So this is going to be 500 milliseconds. And how many seconds is 500 milliseconds? And how many seconds is 500 milliseconds? Right, half a second. So you see, slow clock, it's going to stay at 0 for half a second because that's how long it's going to take for count to equal 50 million, right? When you started at 0 and incremented 1 for every positive edge of the clock. And then once it hits what max count is, it's going to initialize count back to 0 and then flip S clock. See, S clock equal to tilde S clock. That just means it's going to invert it. So after this half second, S clock's going to be a 1. And now S clock's going to remain a 1 for half a second, right? Because it's going to take another 50 million clock edges until it flips again. So you see, this is going to stay a 1 for half a second. And then it's going to go back to 0 for half a second and so on.
Where did we cover, where did we declare S clock?
Right up here, it's the output.
Oh.
Yeah. And then also
Thank you.
see, well, I'm glad you asked, because again, I just want to point out that we not only declared it as an output, but then also we initialized it to 0. Okay, so that's another way you can initialize an output is right in the declaration. Okay, so look, coming into this clock divider is something that has a period of 10 nanoseconds, which has, which corresponds to a frequency of 100 megahertz. Well, coming out at S clock, what's the period of this square wave that's low 0 for half a second and high for half a second? 1 second, right? It has a period of 1 second. Remember, a period's just the amount of time it takes a wave to repeat, right? So you see our period's 1 second. What's the frequency of something that has a period of 1 second? How do you get frequency from period? Yeah, just 1, because it's 1 over 1. 1 hertz. So you see, this is taking a signal, a square wave with a frequency of 100 megahertz, and it's outputting a square wave of 1 hertz, right? So it's divided by 100 million. Okay, so if you wanted to have a clock divider that instead of outputting 1 hertz, outputted say 1 megahertz, you would just have to figure out, well, what does max count have to be to give me that period of a 1 megahertz signal, right? So by changing the max count, you can vary how much this module is dividing that input frequency by. Okay? Okay, so any questions on anything that we talked about this module? Like I said, There'll be a clock divider in lab 6, but we actually just give you that file. You're not gonna, well, you will have to make an edit. You do have to make an edit to the max count integer. And I'll explain why when I talk about lab 6 next week. But like I said, you may need a clock divider for your final project team. Again, it depends on what you decide to do, but a lot of people, find that they need one. So if you need one, or in case you need one, I would hang on to this so you can use this as a reference. Okay, so the next thing I want to talk about before talking about an FSM is a counter. Okay, so there's basically two main points I want to make. One is right here. A counter is just a memory register like we talked about last class after the midterm, plus incrementing the output in some fashion. And here's an example of a counter that's used in the microprocessor that you build in CPE 233. So on each table, I put this diagram that we've looked at a few times this quarter of the CPE 233 microprocessor. And if you take a look at this diagram and you look in the lower left-hand corner, there's a module that's labeled PC. PC stands for program counter. And if you take a look at the inputs and outputs, you'll see we have an output labeled PC out. We got this input labeled PC in. Here we have a PC RST. Can you guess what RST stands for? Yeah, reset. That's a PC reset. And then PC WR. WR is short for write. And write is the same thing, for our purposes, write is the same thing as enable, or enter. So even though these inputs and outputs have these strange names, that you haven't seen in this class, they're really nothing more than something we've already talked about, because PC out, that's just the Q output of a register. PC in, that's just the D input of a register. PC RST, well, that's the reset input. And PC underscore WR, that's an enable. See, when PC write is activated, and this is activated with the 1, well, then Q gets assigned to whatever the D input is. Okay, just like what happens when you load a register or enable a register like we talked about. Okay, so when you model a counter in System Verilog, it's the same code as a register. So, you model a counter same as a register, right? So that code that we looked at after the midterm, right? Remember, the code for a register is the same as a D flip-flop, but you just got multiple bits on your D input and your Q output, right? That we talked about. You would have that for the counter, and then in addition, you would need additional code to get this increment, okay, to get the output to increment. Now here, the amount that we increment the output on every clock edge is this +4. Now, when you take the class, you'll learn why it's +4, okay? My purpose today is not to teach you CP 233 and explain why this is +4. My purpose is just to show you how a counter is very much like a memory register, right? So the way that you would model this +4 is it would just be an additional assign statement to this code you already have for a register. So you would just put assign. Now, I use T1 and T2 for these internal signals. Hopefully when you take that class, you're going to use more descriptive names for internal signals, but here, I'm just using these simple names here. But again, when you take that class, don't use T1 and T2, because you're going to have, when you put this all together, you're going to have like 50 internal signals, and you don't want like T1 through T50, right? Because when you got to troubleshoot this thing and you got 50 waveforms on your timing diagram, and they're like T1, T2, T3, and so on, you're going to be like, where is T15, But if you use descriptive names, like, for example, like T2 connects the +4 to PC in. So you could do like PC in, underscore T4 or something like that. Just so you know where it is by the name. But anyway, with the internal signal names that I have here, to get that +4, you would just assign T2 the T1 +4. Okay, because in Verilog, system Verilog, the plus sign is addition. I mean, that's why we don't use the plus sign in a Boolean equation for or, right? Because it's actually adding with that. So here, we're making the software do the work and come up with the adding circuit instead of us, doing like an RCA. Okay. All right. So any questions about the clock divider or the counter? Counters are also popular in team projects. Because sometimes, like if you're doing a game, you want to keep track of like how many times a person gets something right or wrong or whatever it may be. So you can use a counter for that. All righty, so let's talk about an FSM, and let me move the camera before I forget. Hold on a second. Yeah, I think that's a little bit better. I can go all the way to the, yeah, okay. All right, finite state machine, FSM. Okay, this is what we've all been waiting for. This is what this class is like meant to lead up to. Because here's the high level black box diagram of an FSM. Now this is generic. Okay, we're going to get specific when we do an example, but this is a generic high level black box diagram of an FSM. And it's got 3 modules. Okay, a mixed state decoder, a state register, and an output decoder. So looking at these, or looking at this diagram, you should be able to tell me which modules are combinational and which are sequential. So how can you tell in a diagram just by looking at a module whether it's combinational or sequential? Press the clock. If it has a clock, it's what? Which one? Sequential, right? Right. If it has a clock, remember that means it has memory, okay? And it's sequential. So this is sequential, and these decoders are combination. So on the first day of CPE 233, when you take that class, and the instructor asks you, okay, look at this diagram and tell me which modules are sequential and which ones are combinational, you're going to get them all right, right? Because you're just going to look, and if there's a clock. Now, remember that little triangle symbol, that indicates a clock input. So even though there's not a line there, it's understood that that's a clock input. So anything that's got the little triangle that represents a clock input, those are sequential modules, and any that don't have that, those are combination. Okay. All right. Now, the next thing is what these different blocks represent. State registers, as we talked about, registers have the ability to store data. And here in the FSM, the purpose of the state registers is to keep track where we're at in some sequence of events. I talked about earlier that the reason why memory is important is because in some sequence, you have to first know where you are in order to determine where you want to go next. Okay, so the state registers, they have like where we're at in some sequence of events. The next state decoder, as the name implies, determines the next state, which is where we want to go, right? So it determines where we go next in the sequence, where we go next. Okay, and then the output decoder, again, as the name implies, the output decoder determines what our output is. Now, here is where there's a distinction between two types of FSMs. Okay, you see there's two types of FSMs, and what distinguishes the two types is how the output is determined. Okay, so the two types, there's the Moore, and this is someone's last name, and there's also the Mealy. There's no relation, as far as I know, to Dr. Mealy. This is a different Mealy. Okay, but again, it's a person's name. Okay, if you have a Moore FSM, the output is determined by the state you're in only. Okay, so if you have a Moore output, if you have a Moore FSM, the output is determined by where you're at. Okay. Now, if it's a Mealy, the output is determined by the state you're in and external inputs, or it could be singular. So, if it's a Mealy, it not only depends on the state you're in, but it also depends on either one external input or multiple external inputs. Okay, so that's the key difference. The Moore output's only determined by the state register, because that's what gives you the state you're in. If it's a Mealy, the output's determined not only by the state register, the state you're in, but also by external inputs or input, maybe singular or plural. So in this diagram, this generic diagram, see how I drew some things in black and then I drew these two lines here in red. If you just look at what's in black, that's a Moore, right? Because if you ignore these red lines, the only outputs going into this output decoder is coming from the state register, which holds the state we're in. If you have a Mealy, it's everything in black along with the red. Okay, because if it's a Mealy, the output is determined not only by the state registers, but also by external inputs or input. Okay, so looking at the diagram, the Moore is just black. Okay, the Mealy is black and red. Okay, Dr. Benson, she has like a clever phrase to remember the difference between the two. And her phrase is, a Moore has less. Right? Because the Moore output only depends on the state register, where the Mealy depends on the state register and external input. So the Moore has less. That's how she remembers. So I think it's a clever way. Okay. All right, where are we at? Oh, we're doing good on time. 20 up. All right. Any now this is just like general type of information, right? Kind of like conceptually, basically, what an FSM is, and again, what it consists of. Now we're going to get more specific. Okay, now we're going to get to a specific FSM, and this FSM that I decided to show in class is a counter. Okay, so it's a finite state machine that is a certain kind of counter, and by no means is a counter the only thing you can make with an FSM. You can virtually do anything with an FSM, any type of circuit. As long as you can draw something called a state diagram for whatever you're trying to design, you can make an FSM from that state diagram. So you see, that's where you always start. Okay, the first thing you do if you want to design any type of finite state machine is you draw a state diagram. And you're going to see what a state diagram is coming up here. In this particular counter that we're going to design here in class and draw the state diagram for, it's going to count in this sequence. It's going to go 2, 0, 7, 5, 3, 2, 0, 7, 5, 3, and just keep repeating. Okay? All right, so the first thing, when you go to make a state diagram, you have to first write what's called a legend. Okay, and the legend just describes, what the symbology that's being used in the state diagram. So, what I'm about to show you is sort of the, most popular way of doing a state diagram. I mean, state diagrams can be somewhat personalized, okay, but there are some things about a state diagram that, are always done, okay? And one of the things that's always done is that we use a circle to represent a state. Okay, so in your legend, you'll have a circle. Also in the legend, you'll always have an arrow, a curved arrow like this. And the arrow represents a clock transition. And, it can either represent a rising edge or a falling edge clock transition. If it's a rising edge FSM, then the arrow represents a 0 to 1 transition to clock. If it's a falling edge FSM, well, the arrow represents a 1 to 0 transition. Okay, so FSMs, it shouldn't be a surprise that FSMs can either be falling edge or rising edge, because it has a sequential component to it that has a clock, right? And everything that has a clock, it's either got to be rising edge or falling edge. Okay, getting back to the legend. Inside the circle, you'll usually see a line, and above the line, you put a label, which is just the label for that state. And then below the line, inside the circle, that's where we put more outputs. Okay, we have a more output that only depends on the state. Remember, more outputs only depend on the state we're in. And since the circle represents the state, that's why we put the more outputs within the circle. Okay, because the more output only depends on that state. If we have a Mealy, we put the Mealy outputs outside the circle. Okay, we have another line here, we put the Mealy outputs outside the circle, and then on top of this line, we'll put external inputs. All right, so it kind of makes sense, right, that you would put the Mealy outputs near where you're putting the external inputs, because again, a Mealy output not only depends on the state you're in, but depends on external inputs. Okay? So like I said, state diagrams to some extent can be personalized, and I'll explain some of the personalized stuff that you can do, but this is pretty, in stone that, most people use this symbology that I have up here. Okay? All right, so now we're going to do the state diagram for this counter sequence. Well, each number in my count is going to be a state. So I'm going to have 5 states in this finite state machine. So in my state diagram, I'm going to have 5 circles. And it doesn't matter how you orient the circles. Okay, I'm going to put them like in a ring fashion, but you can put any type of orientation. It can be in like square, rectangle, irregular shape, whatever you want. So I'm going to do it like this. Okay, and I'm going to put in the lines here. And I'm going to label my states just with letters. Okay, like state A, state A, state B, and so on. So I'm going to use ST for states. So state A, state B, state C, state D, state E. And I'm gonna make these numbers in my counter sequence, I'm gonna make those more outputs, okay? I'm gonna make them so they only depend on the state they're in. So those numbers are gonna go inside the circle. And I'm gonna write those numbers as 3-bit binary. I mean, I could write them as base 10, but I just decided to do it as 3-bit binary. So 3-bit binary for 2, 0, 1, 0, for 0, all zeros, for 7, all ones, for 5, 1, 0, 1, and for 3, 0, 1. So now I'm going to get more specific, right? I was general by just putting more outputs here, but now since my more output is 3 bits, I'm just going to show it as, you know, B2, E1. Right? Okay, so now, you see, I'm going to start off with the simplest type of, you know, state diagram you would see for an example like this, and then I'm going to make it a little bit more practical and a little bit more involved. But the most basic type of state diagram for this particular example is that I would just, on every clock edge, I would just transition to the next state. So I'm starting at state A, where the first number is 2. And once I get a clock transition, while I'm in state A, when I get a clock transition, say a 0 to 1 transition of the clock, well, then I'll go to state B. So you see, this represents like a 0 to 1 transition of the clock. This transition is going to happen from A to B. And then the next clock transition, 0 to 1 transition, I'm going to go from B to C. And then the next clock transition, 0 to 1, I'm going to go C to D. Next 0 to 1 transition to E. Next back to A, because it just repeats. So if you don't see anything next to a transition, right? Like there's nothing there, that just means it's unconditional. And unconditional means that once the clock edge happens, you're going to get the transition from to the next state. Okay, so again, this is like the most basic state diagram you could have. But now let's make it a little bit more interesting, a little bit more practical. In a practical design, you would probably have a reset. Okay, so in your legend, if you have a reset, you would show that like this. Okay, just an arrow going into the state. And I'm going to make this an active low reset. And also, I'm going to make it asynchronous. Now, and make sure you take note of this. So when you take CPE 233, you don't tell the CPE 233 professor the wrong information, so I don't get yelled at. The only reason I'm making this an async reset is for an academic reason, because I haven't shown you yet how you would model an async input in System Verilog. I've only shown you how to do modeling of synchronous inputs. And what you'll learn in CPE 233 when you build that microprocessor is that reset is, I think I can say in this case, never asynchronous. In any sort of practical design like that microprocessor where you have reset going to virtually every module, you want the reset to be synchronous. Because if reset is synchronous, where it's going to multiple things, it's more likely, because it happens right on the time of a clock edge, it's more likely that it's going to reset those modules all at the same time, or virtually all at the same time. Where if you have asynchronous resets, there's more of a chance that you'll get a time delay between when modules are reset, and that can cause all kinds of problems. Okay, if you're not resetting everything at virtually the same time. So again, please, when you take CPE 233, don't say, well, PERC's use an asynchronous reset. Again, the only reason I'm using that is for an academic reason. Okay, if this was a practical, counter circuit, I would not make that asynchronous. Okay, all right. Just wanted to make sure that was clear. Now, I have decided that if reset is activated with the low, remember that bar means it's active low, it's going to take us to state A. So I would just show that in the state diagram like this. Okay. All right, now to make it more interesting, I'm gonna add an external input. And this external input that I'm gonna add is an enable. And I'm gonna make it an active high. So when this enable input is activated, when it's a high, we'll proceed to the next state. If the enable is not high, if it's low, we're just going to stay in the state we're presently in. So the way I would show that on the state diagram is that for each transition, I would show En, meaning that when En is a 1, that's when we're going to transition from A to B. And I would do that for all the clock transitions here. And to show that if enable is not activated, that's a low, I'm just going to show an arrow that goes back to the same state. So if I'm in state A and the enable is not activated, if it's low, I'm just going to stay in state A. Okay, if I'm in state B, right, and enable is not activated, it's low, I'm just going to stay in state B. Right? And for all these states, same thing. If it's not activated, I just stay in the same state. Okay, so you see if it's enabled, I proceed, right? If it's not, I just stay in the same state. Now, here's where the state diagram can be personalized a little bit. See how I'm using the variable without the bar to mean a 1 and the variable with the bar over it to represent a 0? You could just actually write here 1 and 0 instead of writing the variable. Okay, that's another way to do it. Like some people just like to put in the 1s and 0s, and that's fine. Okay, so that's some personalization that you can do. All right, so you see in our legend now, this is generic, but now we can be specific that our external input is En. Okay, all right, so now let's add a Mealy output, because you can have an FSM that has both outputs, that have Mealy outputs and also more outputs. Okay, so here the count is a more output, but now I can choose a Mealy output, and in this case, I'm gonna make an LED a Mealy output, and I'm gonna light that LED when the sequence starts, and I'm gonna light that LED when the sequence ends. Anything else, I'm gonna turn it off. So the way that I would show that in the state diagram is that right here, right, underneath the external input, you put a slash and then LED. So I'm starting the sequence here, I'm gonna light the LED, and then over here, when the sequence ends, or when it repeats, I guess, because it just keeps repeating, I'll light an LED there. But everywhere else, I'm going to turn off the LED. So if I just stay in state A, I'm going to turn it off. Right? If I just stay in state B, I'm going to turn it off. If I'm going from B to C, that's not the beginning or the end of the sequence, so I'll shut it off there too. I'm going to shut it off everywhere else except where the sequence starts and where it ends. Oh, let me move right here. Make sure that is. So I think I got them all, right? Because LED on when it starts, LED on when it ends, LED off everywhere else. Okay, so that's a state diagram. Now, we're going to take a break here in a moment because it's going to probably take me a good at least 20 minutes, maybe 30 minutes to show you the code for this. But before we take a break, one more thing, unless you have questions, and that's let's make the high level black box diagram for this counter FSM. So remember, the high level black box diagram, it shows you the main inputs and main outputs for your module. So you should be able to tell me what my main inputs are for this FSM and what my main outputs are. You want to give me an input or output? Just by looking at the state diagram.
Enable.
Enable is an input, right? That's an external input, so yeah, enable. Put enable here. Any more? What is it? Or reset, restart, yeah, RSD. Any other inputs? Very good, yeah, because remember, FSMs, they have a sequential portion, so they always have a clock input. So yeah, those are all our inputs, enable, active low reset, clock. How about outputs? LED, very good. What else? There's one more output. The main output. What is this thing doing? That's, yeah, the 3-bit count, right? Or more outputs or 3-bit count. Right, so you see, those are our main inputs and outputs. So when we model this FSM in System Verilog, well, just like any module, you have to declare the inputs and outputs. So you would declare these 3 inputs and those 2 outputs. Okay. All right, so we're just about at the top of the hour, and this is a good part of the lecture to take a break. So why don't we take about a 5-minute break? I'll start up like around 5 past, and I'll show you the System Verilog code that you need to model this FSM. And what you're gonna see is that once you have a state diagram, to write the code that you need, it's very cookbook. Okay, it's very cookbook. Okay, but like I said, let's take about a 5-minute break, and I'll pick up with this when you come back. Oh, okay. Well, if you're not feeling well, that's the university recommended excuse. Just get like a note or something. Like if you go to the health center and just say, we're seeing you, that would be good.
I just have a massive headache and can't focus on this.
Okay. Well, yeah, if you miss a class and I don't get documentation, I mean, it's like a 1% hit because each activity, well, the total amount for activities is 15%. There's 15 of them, so it's just 1%. You won't worry about it. But yeah, if you're not feeling well, I wouldn't stay here.
Probably not, I think so. Six. Yeah. Two. I think. Perhaps these is. Yeah. But actually. Yeah, some of them, yeah.
Okay, so let's go ahead and finish up today. So we've got our state diagram for this FSM, and like I said, that's where you always start. You know, I can't tell you too many times, you know, because the FSM is part of Lab 6, and also you'll need to do an FSM for the final project individual and also the final project team. A requirement is that you got to have an FSM. So, you know, you're going to be doing 3 state diagrams. And I can tell you how many times, like for the final project, somebody will be having some difficulty and they contact me. And the first thing I ask them, they go, well, can I see your state diagram? And they go, oh, wait a minute, let me write it down. Right? Because they're trying to keep it all in their head. And, you know, most people, you're going to make a mistake if you don't write it down. So, you know, just start by writing it down. So like I said right before the break, you know, like any module, and no different with the FSM module, you got to declare your inputs and outputs after you have the name of your module. But now what's different and what you haven't seen before is that when you're doing an FSM model, the next thing that you would put after you declare your inputs and outputs is the following. You would put type, DEF for definition, that's short for definition, and then ENUM, which is short for enumeration. And then inside braces, you would put the names or the labels of your state. So since I have state A, you know, through state E, that's what I would put here. State A, and you separate them with commas. G, state C, and so on. Just put all your state labels, and then you close the braces, and then you put states with the semicolon. And then under that, you put states. And then PS, that stands for present state, comma, NS, that stands for next state, and then semicolon. So what this 2 lines of code is doing is that it's defining your states and also the number of states. And it's also defining, you know, what's called present state and next state. And you'll see how this fits into, you know, the rest of the code coming up. Now, before I go any further with this, I want to make a comment about the activity. Because see, on your table, each person could have this hard copy of the activities. And here in class, I'm showing you how to write the system Verilog from a state diagram. In the activity, I give you the system Verilog and I want you to show the diagram. So the activity, you're going the opposite direction of what I'm showing you in class. But if you understand one direction, you should be able to go the other direction. But the thing I wanted to point out in this activity code is right at the top, okay, beneath where it says output logic Z1, Z2. Okay, so below that and above where it says always FF, you see there's those 3 lines of code, parameter 1 to 0, STA, 2 tick mark D0, you know, SB, so on. And then it has internal signals for NS and PS. Well, those 3 lines in the activity essentially do what these 2 lines do. Okay, there's 2 different ways of doing the same thing. So you can use this method where you're enumerating these states with the label names, or you can do it this way, which is more brute force, where you're assigning each state the number of bits that it takes to represent that state. Like state A here is state 0, so that's why you see 2 tick mark D0. and state B is binary 1, state 1, and so on. Okay, so the reason I show you both, right? The reason you see a different way on the activity compared to what I'm writing on the board is because, in my opinion, this is the better way to define the states than what's on the activity. And the reason why I think it's a better way is because if you use this method of defining the states, the one that's on the activity, if you have to edit your state diagram, like say you have to add states, like maybe you start off with 4 states, but then through the process of doing your design, you realize, oh, I can't do it in 4 states. I need 8 states. Well, if you add states or do any sort of editing to your states, you have to change this manually, right? Because now if I got 8 states, can I use 2 bits to represent 8 things? No, I mean, how many bits do I need to represent 8 things? Well, the minimum number, 3, right? So I'd have to change all these to 3-bit. And, it can just be a pain, especially when you get something, complicated with a lot of states. Well, this way of defining the states, if you edit your state diagram and you either add or delete states, the software does it for you. The software figures out what the new numbers have to be, the new binary bits have to be. Okay, so that's the advantage of using this syntax to define your states. Okay. Okay, so now let's do the rest of this. So let's see, I gotta find my notes here. Oh, here we go. All right, so after you declare or define the state, now we're going to write system Verilog that should be somewhat familiar. Yeah, before I start writing, just a little review here. When we have a sequential circuit, like when we did the modeling in system Verilog for the D flip-flop and also the register, right? The last class after the midterm. What kind of block did we use if it was sequential? Like we had an always. Say that again? Always. Right, it's always FF, if it's a sequential logic circuit, right? And then when we were doing combinational, like the decoder in lab, what was it? It was lab 3 and also lab 4, or no, just lab 3. And then like the mux, right? Remember we had an if statement for the mux and a case statement for the decoder. That went inside an always home, right? Because it was combination. So look, the FSM is made of sequential and combination. So what you're going to see is that there's an always FF block and there's an always home block to model an FSM, right? And that should make sense because looking at this, it has both types. Okay? So you always start with an always FF. So after you declare the states like we have here, we put always underscore FF. Then we get the @ symbol. Okay, then in parentheses, we're going to have positive edge clock because this is going to be a rising edge FSM. Okay, now this is something new, and this has to do with making the reset asynchronous. Okay, so if I want to make that reset an active low asynchronous, I would also have to add within the parentheses here a neg edge. Oh, excuse me. The neg edge reset. So neg edge RST. Now I'll come back and I'll explain why you have to do that. All right. Right now, this is what inside the parentheses would look like. Okay, then we're going to have a begin. And then if. Okay, if, and then inside parentheses, an exclamation point, and then the name for my reset, which is RST. That exclamation point, that knots this. See, if the exclamation point wasn't in there, that would be an active high reset. To make it active low, you put an exclamation point before it. So the exclamation point within an if statement is the same as a tilde in a Boolean expression. Okay, when you want to invert something in a Boolean expression, use the tilde. If you want to invert something inside an if, you put the exclamation point. That's just how System Verilog is designed. Okay, so if our reset is low, we want to go to state A. So the next thing you would put is present state assigned to state A. Right? We labeled state A, STA, we declared it STA up here. Okay, so remember that inside and always FF, when you assign an output of value, you use the less than with the equal signs. And remember that's the symbol you use within an always FF. If it's an always COM, you just use an equal. Okay. Okay, so if reset's active, if it's low, we're going to have our present state assigned to state A. Else, present state is just going to be assigned to the next state. Then we need an N. Okay, so if we're not resetting, then we're going to determine what the present state is by the next state. And as you're going to see in a moment, the next state is determined by an always COM block because the next state is determined by a decoder, and a decoder is combination. Okay, so the next thing is, okay, why did I put the negative edge reset here, the RST? Well, if I didn't have it, okay, if I just had in parentheses the positive edge clock, remember that whatever's inside the parentheses, that's when what's inside the always FF will be evaluated. So if I only have positive edge clock, this if statement within the always FF is only going to be evaluated at the time of the 0 to 1 transition of the clock. So if I just left this as positive edge clock, that's going to make this reset an active low synchronous input. Okay, but by adding this negative edge reset, now this always FF block, this if statement, is going to be evaluated on the positive edge of the clock, and also anytime we have a negative edge of the reset. So on the 1 to 0 transition of the reset, like if we go to make it low, this will also be evaluated, and if it's going low, when it gets evaluated, it will be low, and the reset will happen. Okay, the reset will happen no matter what the positive edge of the clock is doing. Okay, and that's asynchronous. Okay, so again, summary, if you wanted this reset to be synchronous, you would not have the negative edge reset. You would just have the positive edge clock. But to make it asynchronous, you add this. Okay. And you know, if this was an active high reset asynchronous, you would make this a pause edge reset. Okay. All right. So first comes your always FF in. You know, for any FSM that you're designing, this is what the always FF is going to look like. You know, typically you'll have a reset, but sometimes you might have an FSM that you don't need a reset. And if you don't have a reset, the only thing you're going to have within the always FF is just PS assigned to the next state. Okay, so what's inside the always FF for the FSM is fairly simple. Okay, the reason I bring that up is I think sometimes students think this has to be more complicated. So a lot of times what I see is that things that are in the always COM that we're going to do next, they try putting in the always FF. Okay, and it doesn't belong there. This is the only thing that belongs in an always FF. It's a reset along with, well, if you're not resetting, then you're going to assign present state to the next state. Okay. All right, so after the always FF, that's when you have the always COM block. So always underscore COM. And you need to begin for this. Okay, and the first thing I'm going to do in this always COM is I'm going to initialize my outputs to 0. Okay, so we have two outputs, count and LED. So I'm just going to put count, assign it to 3 zeros. And let's see, you got to put a semicolon there, and then LED assigned to 0. So this is just initializing the outputs. Initialize outputs. Okay, now I'm gonna have a case statement. And this case statement is gonna be sensitive to present state, PS. Because remember, whatever you put inside the parentheses of the case statement, when that changes, that's when the case statement gets evaluated. So if we're not resetting and present state gets assigned to next state, that's when it changes. And now we're gonna evaluate the case, which is gonna give us what the next state is. Okay? All right, so that's, well, let me now go up here. Okay, so now we're gonna have our options in our case statement, right? Remember when you did the case statement, like for the decoder, right? After you have the case with what it's sensitive to, then you just list your options. And our options in the case are gonna be our states. Okay, so you would just put state A. Okay, you put a colon. Okay, you need a begin. All right, the first thing you put, okay, after you put the state label, right? Colon, then begin. The next thing you put is what the more output equals to that state. Okay, so this is where I'm just looking at my state diagram. And remember, the more output is within the circle. Right, so for state A, the more output is equal to 0, 1, 0. So that's what I put right after this. I put count equal to 3, tick mark B, 0, 1, 0. Right, so this is the more output. See, the reason why you put the more output right after the state is because that's all a more output depends on. It only depends on the state you're in. So once I'm in state A, I know that this more output is going to equal what I put inside the circle. Okay? All right, so now the next thing comes the Mealy output, right? Because the Mealy output is conditional, right? Our Mealy output here is LED, and it's conditional on this external input, EN. So like we said earlier, a Mealy output depends not only on the state, but it depends on an external input. And in this case, the external input is enable, EN. And you see, we're going to use an if statement, right? Because if EN is 1, we're going to light the LED. If EN is not 1, we're going to shut the LED off. So we're going to have an if statement within the case. It's like a nested if within the case statement. Okay, so I have if, enable, and I'm going to need another begin here for if. Okay, so if enable is 1, right? See, I'm looking right here. If enable is 1, we're going to turn the LED on and go to state B. Right, so LED on, so I'm going to make that a 1. And then next state, I'm going to assign to state B. And then I got to end this. Right, this end goes with this begin right here. Okay, so if enable is 1, LED on, and I'm going to state B. Okay, that's what that part of the code does. So you see right here, that's a Mealy output. See, when you look at this FSM code, if there's an output within an if statement, it's Mealy. If it's outside the if statement, like this output count, it's a more. Okay, that's how you tell the difference between the two, just by looking at the code. Okay, then I need an else. Right, because if enable is not 1, right, if it's 0, I'm going to shut the LED off and I'm just going to stay in state A. Right, so for the else, we would make LED equal to 0, and then next state would just equal state A. And I'd have to end this. Let's see. Losing track of my ends. This always happens. Oh, I don't have a begin for my else. There should be a begin. Sorry. Got this. So you need a begin for this port. You know, this begin end is for this portion of the if, and then I need another begin end for this part of the if, the else part. Then I also have to end this, let's see, this is for that, that is for that. And then I need an end for the state, or the option, you know, the option of that case state. Yeah, usually when I make mistakes with this, it's, I either have too many ends or I don't have enough, so you just gotta keep track. Like every begin needs an end, so you see this end goes with that begin. This end goes with this begin, this end goes with that. Then we're gonna need another end eventually for this begin. Okay, but any questions about what I wrote for state A? And can you see how I'm just looking at my state diagram to get what I need to the code? Okay, I'll do one more state. I mean, if you want me to do more after I do the next one, I will, but I think, you know, 2 should probably be enough and you'll get the idea because it's just repetitive. So now I would have state B. And again. Okay, look at state B. And my more output is all zeros. Okay, so that's the first thing I put, right? I put count equal to 3, tick mark B, 3 zeros. Again, that's my more output for state B. Okay, now I have an if statement. Right, so I'm here at state B, so if enable is a 1, I'm going to turn the LED off and go to state C. Right, so if enable the 1, and I need it again here. LED is going to be off, so I set it to 0. And next state is going to be state C. And then I got to end that. Okay, else. Okay, so, you know, state B, so if EN is not a 1, if it's 0, I'm going to turn the LED off and just stay in state B. Okay, so that's going to be LED off, so LED equal to 0. And next state equals state B. Oops, that's semicolon. Right, and then I need an end for that begin and another end. And then for that begin and another end for this begin. All right, so you see how it's repetitive? It's the same order of things, just like it was for state A, right? It's just, again, I'm looking at the state diagram to get what LED is equal to and what my next state is equal to. Do you have a question?
Yeah, is state B within case present state,
Well,
or should it be in a different case?
no, it's all of this is within one case. Because again, when we're not resetting and present state gets assigned to next state, it changes. And that's what activates the case, so to speak, right? Because whatever you put within the parentheses of the case, when that changes, that's when what's inside the case is now going to be evaluated. Okay. Yeah, so this is state A and state B. Now you're going to need a whole nother, section of code for state C, D, and E. And I'll well, you don't have to actually figure it out, but if you were going to model this whole thing, you'd have to figure out, what I did here for state A and state B for C and D and E. Okay, so let's say you do that. Let's say you fill in the rest of this, and you're at the end of state E. Like you got the 2 ends. Like see how we got 2 ends at the end of state A, right? 2 ends at the end of state B. You would have the same thing for state C, state D, and then at E. This would be the end of state E. Okay, what would we put next? Because remember, this is all within a case statement. And what do you always have to end the case statement with? A what? I think I heard it. a default, right? So once you're done with the options, it'd be 5 options here for the case. You got to make sure you put a default. And you can make the default whatever you want. I made default next state equal to state A. Right, that if we hit the default, it's just gonna take us to this first state here, state A. Okay, now again, you can make the default anything you want, but why do we want the default? Why would it be a bad thing not to have the default there? Because what would it create? What happens if you leave an else out of a if statement? Create the latch, right? So same thing with a case statement. If you leave out the default, it's going to create a latch. And you don't want a latch because this is combination, right? Inside an always comb, you don't want to create a latch because, again, we don't have memory and combinational circuitry. Okay, so after this default here, we would have to end the case. So end case, right? So you always need an end case, and then we need another end for this begin. So after the end case, we have an end for the always home block, and then we have an end on. Okay, so this is the format that you use to model any sort of FSM in System Verilog, and hopefully you see the importance of the state diagram, because once you have the state diagram, it's pretty cookbook to get the System Verilog. You're just following the same procedure that you saw me go through, right? The more output is the first thing you put, okay, inside an option, a state option inside the case. And then a melee is going to be conditional, so its output is going to be within an if statement. And then to get what the next state is equal to, you just got to look at your state diagram to see where you would go based on that input condition. Let's see, anything else? I think that's all that I wanted to say. Do you have any questions about any of this? Like I said, the activity is going the other direction. Okay, you're given code like this, and we want you to write the state diagram. So, you look at the code, you see what are inputs, right? Because, well, in fact, let's look at the state diagram. Or let's look at this activity. So looking at this activity, what are the inputs to the FSM? How many inputs are there? There are 3? 4, right? Because you got clock, X1, X2, clear. So X1 and X2, those are your external inputs. Okay, how many outputs do we have? 2, Z1 and Z2. Now again, the next 3 lines, the parameter line and the 2 logic lines, that's just defining the states. Okay, other than the labels, it doesn't really give you any information as far as the state diagram goes. I mean, the labels tell you that there's 4 states, and they're labeled STA, STB, STC, and STD. So how many circles are you going to have in your state diagram? 4, right? Because STA, STB, STC, those are your 4 states. Okay, then you look at the always FF. Is, well, that clear input. How would you describe it? What is it activated by? A 0, because it's got the exclamation point in front of it. Remember, clear is just like reset. Is it synchronous or asynchronous? Async, because it's got the negative edge CLR. Okay. Let's see, what else? All right, and then when you look at the always comb, you can see that the outputs are being initialized to 0, and then you got the case statement. So you got 2 outputs, Z1 and Z2. Can you tell me whether they're more or mealy by just looking at this code? You should be able to. Z1, is it more or mean? Why?
That's what I get.
Is it
Outside the case statement.
Well, remember
the
that-
initial says.
Well, it does, like here. You know, we initialize count and LED outside. Right, and one of these is more, one of these is more, so where you initialize, well, you always initialize before the case, but that doesn't determine whether it's mealy or more. What determines whether it's mealy or more? Yeah, if your output is within an if, it's a mealy. If it's outside the if, then usually right after the option for the state, that's a more. Okay, so which one of these is a more, Z1 or Z2? Z1. Right, because you see how Z1 is above the if statement? And you see how Z2 is within the if statement? So Z1 is a more, Z2 is a mealy. Okay, let's see, is there anything else here? I mean, the rest of it, you should be able to determine, you know, how the transitions go from, you know, looking at the if statement. Also, I mean, what's a little bit different in this activity is that you have two external inputs instead of just one, right? This example just had enable as an external input. Here you have X1 and X2. So what you might find out is that one or both of these inputs, okay, external inputs, may not matter in all cases. Okay, you may have a case where, or you may have cases where the transition, like where you go from one state to another, only depends on either X1 or only depends on X2. And if that's the case in the state diagram, you would show the input that doesn't matter with a dash. Right? Because remember in K-maps, we would show outputs that don't matter with the dash. Well, you can show inputs that don't matter with the dash too. Okay. But other than that, I think you should be ready to do the activity. Any questions before you get started? Okay, so work on the activity. Once you're done with that, I would work on the labs. Remember, lab 4 is due tomorrow. Lab 5 is not due until a week from tomorrow. And then lab 6 will be due November 17th. That's the Friday before Thanksgiving break. But you don't have enough information yet to do lab 6. You will after Tuesday's class. Okay, Tuesday of next week. Okay? Great. Use.